always have to remove the effect of EI on y double prime. That's why I always write it this way. Y double prime plus 2p over EI times y1 equals MA over EI. Now let's define a new buckling parameter, and let's call this, because we have y1 and y2, so why don't we call this one k1? Let's call this k1 to be square root of 2p over EI. Now with this, let's go to the next page. With this, I'm going to continue here. The equation becomes y1 double prime plus k1 squared times y1 equals MA over EI. Right? So that's our step 1. And step 2.
Professor, can you go back a little bit?
To what here?
Okay. Okay. Yeah.
Oh. Actually, I catch this one here. Let's not forget about those subscripts. They are important because we have 2. Of course, there's one more, right? This one here. Let's not forget about it. That's y1. And then step 2, we just solve it. And from differential equation, we know that the complete solution, y1 of x1, has 2 components, yc plus yp. So this is going to be y1c plus y1p. And I will just give you the final expression, and that is a1 times the sine k1 x1 plus b. Well, we actually don't have to put subscript for a and b, so we can just leave it. A is the only one a. There's no a1, b1. I'll just use a, b, c, d. Plus b times cosine k1 x1. That's a complementary solution. For the special solution, particular solution, you just have to divide and the constant term, as long as it's not x associated, x variable dependent, divided by with k squared. And that will give you plus MA over EI over K1 squared. Now, if you like, you can also write it differently, because we know that K1, what's K1 squared? Well, K1 squared is just 2p over EI, right? Of course, just some discussion here, because K1 squared is 2p over EI. So you can also write that MA over EI over K1 squared to be what? To be MA over, what's that? 2p, right? Just 2p. You may notice that in some of the examples I did before, I use the other expression, but mathematically, these two are identical. You should notice that. What I'm saying is this and this, they are the same. Same thing.
Professor, can you just clarify something really quick? The sine K1 and X1, is that sine of K1 times X1, or is that sine of K1 times X1?
That is always sine of K1 times X1. And
so that whole thing, it's sine of that whole thing?
Yes.
Okay, awesome. Thank you.
Sure. And for the reason I explained before, if I write this way, every time I write this way, there's a lot of parentheses I'm going to write in my equation. You know, I use extensively with the trigonometrical equation functions. So that's why I don't put this parentheses unless I need to distinguish one from from some special cases. Otherwise, I'm not going to write down this parentheses. Okay. All right. So now we can. Now, once we have this expression, what we have to do is just plug in the boundary conditions and just write down boundary condition and find it. In this case, you already know boundary conditions very well. I don't have to explain everything to you, right? You know that y1 when x equals 1 to be 0? Because it's a fixed ended. Because it also is a fixed ended, the slope has to be 0 as well. So that means y1 prime at x1 to be 0 must also be 0. Okay? And from this definition, which is this profile, you know that x1 is from A to B. And x2 is from B to C. So when x1 equals half of the total span, which is L over 2, y1 is actually delta B. Would you agree? Would you agree? Because y1 is just a horizontal deflection, right? So when x1 is arrives B, point B, which means x1 becomes L over 2, y1 becomes delta B. Correct? So that's what we know. And that's what I'm going to write here. This way, I'm just going to write y1 when x1 equals L over 2, this equals to delta B. Now, since we are on this, you might have just also figure out what is the boundary condition right here. Now, for the other one, you have to be careful because for x2 and y2, we use this. We move it actually a little bit, right? And that means what? That means there's already a coordinate shift at x2 and y2. We don't know that yet, but at least we know with y2 at L over 2. And can anyone tell me that what is the deflection here?
Zero. Zero.
No. Y2 is this. How can this be 0? This is y2. Deflection, not slope. Deflection. Even slope is not 0, right?
Is it equal to delta B?
Delta B is for x1, and x1 will end at here. x1 is from, this is x1 and y1. So this is x1, this is y1, right?
It's delta C minus delta B.
Says who?
That's y2 at L over 2.
Very good. You're right.
Because you moved the coordinate system
Look at
L
this.
over 2
Yeah,
on
look
the
at this.
extra.
Okay. So when x1 at L over 2, y1, notice that the thick red line, right? That is the value of y1. However, for y2, you don't have the whole thing. You have to remove the coordinate shift. And that means it's not the whole thing, but it's only this part. Would you agree? Would you agree?
Yeah.
Okay, so that's why back to here, I'm just gonna write down this. So this equals to delta C minus delta B. Okay, and we're gonna use that later on because we are still dealing with x1 and y1. So let's solve the x1, y1. And of course, you know how we plug in the mathematics, right? So the way we're going to solve it is you plug in the coordinate conditions. The first one, use this. When y1 and 0, what you do, that means you have this. This will give you 0 equals sine 0 is 0, so it's A times 0, plus cosine 0 is 1, plus B, plus MA. Of course, you can write either way, and it's 2P, I think it's easier. Correct? And this has to be 0. So from here, what do we found B? We can determine B, right?
Negative MA over 2B.
Very good. So A is gone, just remember that. And so from here, B equals to negative of MA over 2P. Of course, I'm going to repeat the same expression because in the textbook, it uses different expression, and it uses MA over EI over K1 squared. But from my explanation, you should know that they are identical. Okay. So this is how we found B. And similarly, we can also find A. We find A by using this, by using the slope condition. From here, that means you have to differentiate it. And of course, it's not that difficult, so why don't we just practice, because that's the first one. And the second example, I'm not going to do it again. For the first one, we can just do it. Differentiate sine, you get to take the coefficient out, and that becomes K1 times A times cosine K1x1 minus K1 times B times sine K1x1. Then what?
Nothing.
Nothing. Good. So we plug in 0 into here, and then what do we get? We get that 0 equals what? K times K1 times A times 1 plus 0, right? This is actually B times 0. If you like the whole package, that's K1 times B times 0. This whole thing has to be, what do we learn from here? A must be 0, right? So we found A 0. All right, Pascal, you have to write. You're not going to learn this if you don't follow my writing. You cannot understand this just by reading, looking at it. You have to write it. Okay? Because I happen to see you. No particular reason. All right. Okay, now let's continue. So we found the total final expression for that. And next one, step 3, is we're going to use the free body diagram to find out the expression for y2. So that means the FBD for member BC. It's going to be something like this. So we will use the same color that we did before. Use this. That means it's something like that. Of course, it also continues deflect going like this.
Professor, isn't this step 4?
Yes, I think you're. It's all right. If this step 2, that cannot be step 4. Can it?
Oh, I thought step 2 was solved, like at the bottom.
That's all.
Okay.
This is step 2 here, right? So what we're doing is step 3, correct? Right? I take that as yes. And right here, this is y2, x2. And this point is point B. And this point is point C. So right here, you have a force acting at point C. You have another force acting at point B. This is member BC, correct? And what do we know? Of course, there's also another internal moment, which is right here. What about the force? What will be the direction here?